Hi, everyone. Welcome to the final talk in this ATIC seminar series for this quarter. Today, we are very happy to have Louie Putterman from Harvard University giving a talk on sparsifying CSPs. He is a second-year PhD student at Harvard, advised by Madhu and Salil Vadhan. And yes, thanks, Louie, for giving this talk. Over to Louie now.
Yeah, so thanks for having me. And so today I'll be talking about sparsifying CSPs through the lens of code sparsification. And this is joint work with Sanjeev, who's at UPenn, and then Santoshini mentioned my advisor, Madhu, who's at Harvard. So first, I guess, what is sparsification? So in this talk, when I talk about sparsification, this is kind of alluding to a broad concept, which is can be thought of as being like somewhat similar to compression. So specifically, we'll be given some data structure X, as well as some class C of queries. And the goal is to create some sparse representation of X, such that for every query Q in this class of queries, the response, or like the return value for this query on the sparsified version of X is preserved to some 1 plus or minus epsilon multiplicative factor. The reason this is going to be like a non-trivial notion is that the size of the set of queries will be exponentially large. And this means that it's kind of a fundamentally different notion than some kind of lossy compression, where lossy compression will only give you a multiplicative guarantee for some like polynomially large set of queries. That said, it's also slightly different from exact compression because we are allowing some error in the response to the queries in the sense that we only have to return a 1 plus or minus epsilon like multiplicative factor. In this talk, we'll also kind of have this nice additional feature that the sparse version of X is still an instance of the same data structure. So what this means is that if you had some algorithm that could run on X, you could also run it on this sparsified version of X without having to change any of the intricacies of the algorithm. Kind of like a seminal example of sparsification is just that of cut sparsification. So cut sparsification, all this means is that we're given a graph G with vertices and edges. The query will just correspond to some subset S of the vertices. And the response that we want for any query is just the size of the corresponding cut. The size of a cut is just, we put vertices in S on one side, the vertices in V minus S on the other side, and we're just measuring, what's the weight of the edges that are crossing from S to V minus S. So in this diagram, right, we have the S on the bottom, V minus S on the top. The response would just be what is the weight of the edges that go from S to V minus S. So it turns out that for this like algorithmic paradigm, the question of cut sparsification would be to return some reweighted subgraph G prime of G, such that for every query, and again, the queries are subsets of the vertex set, the size of the cut in G prime is preserved to a 1 plus or minus epsilon multiplicative factor with respect to G. So in this diagram, for instance, we've somehow taken this graph on the left, we've created a sparser version in the sense that lots of edges have been deleted. The surviving edges have been reweighted to kind of compensate for the fact that we deleted some edges. But still, if we look at any like partition, any subset S of the vertices, the number of edges that's leaving this set has been preserved to some multiplicative factor. It turns out that, do some beautiful work of Karger in the 1990s. This is actually like a very general property. So in particular, for every graph on n vertices, we can sparsify it to like essentially a linear number of edges. Really, we're hiding some log factors like O tilde n over epsilon squared edges, while still preserving the weight of all 2 to the n cuts to within a 1 plus or minus epsilon factor. And this is very non-trivial because we've gone from a standard graph, which can have as many as like order n squared edges, so order n squared bits to describe the graph. And instead, we've created a representation which has only a linear number of bits required to represent. Yet still, for every possible cut, and there's again 2 to the n possible cuts, we have like preserved the size to a 1 plus or minus epsilon factor. Not only this, but Karger also gave an algorithm which computes such a sparsifier in near linear time in the total number of edges in the graph. So you can tell this is going to be a very useful paradigm for like many downstream algorithms. And in general, if you're concerned about space, for instance, in space-bounded derandomization, this kind of paradigm of sparsifying the graph is very useful. So naturally, people then started asking, where else does this paradigm apply? Where else can we perform this kind of sparsification? So kind of one prominent line of work that came out of this was talking about sparsifying hypergraphs. So in this setting, we're given a hypergraph. The only difference with respect to a graph is that now the hyperedges don't just have to be of size 2. The hyperedges can, join an arbitrary number of vertices. We can still define cuts in a similar manner as we defined in a graph, in the sense that a hyperedge E will be cut by some set S if the hyperedge E is crossing from the set S to the set V minus S. So in this diagram on the bottom right, for instance, the yellow hyperedge would be considered cut because it's crossing from the set S to the set V minus S. The red hyperedge would not be considered cut because it's completely contained on one side and it's not crossing. And it turns out that even with this definition of cutting, which is we're capturing a much broader class of data structures than just with ordinary graphs, there still exist these O tilde n size cut sparsifiers. And this kind of begs the question whether there's like a broader class of objects, of combinatorial objects that we can hope to sparsify. And if so, what is this class of objects? What does it look like? And more importantly, like how do we represent this class of objects? And it turns out this question was already at the heart of works in the 2010s. And in particular, this work of Kogan and Krautgamer in 2015 came up with a very nice paradigm for generalizing all of these kind of cut sparsification phenomena. So this phenomenon was called CSP sparsification. And the observation is that, for instance, if we talk about graph cut sparsification, it has a sort of canonical representation as a CSP. And so what do I mean by this? If we're given a graph G with vertices V and edges E, for every edge, and say the edge is crossing between two vertices U and V, we can instead create a corresponding constraint, which is just an XOR constraint between the two vertices U and V. So again, here, for instance, there's an edge between vertices 2 and 3. So this would mean we add an XOR constraint, X2, XOR, X3. The point now is that for any possible cut in the graph, so we think about this cut as being all the vertices to the left of this red line, if we assign a value of 1 to all the variables inside the cut, and a value 0 to all the variables outside the cut, each edge will be cut if and only if the corresponding constraint evaluates to 1. So the way to see this is that, for instance, the edge between like vertices 2 and 3, the only way this will be cut by a set S is if one vertex is in the set S and one vertex is not in the set S. In particular, this means for this kind of canonical assignment, one vertex would have to be a 1 and the other vertex would have to be a 0. So when we look at the corresponding XOR constraint, the XOR constraint will be 1 if and only if the corresponding edge is cut. So naturally then, this question of sparsification, where again, we want to preserve the size of every cut with some kind of reweighted like sub-instance, just corresponds with the property of choosing a weighted like subsample of the constraints in this constraint satisfaction problem, such that for every assignment X, the weight of the satisfied constraints is preserved. So again, the correspondence is that edges in the graph have now become constraints in the constraint satisfaction problem. The queries, which were originally subsets of vertices, are now just bit strings, like assignments to the variables. And we want to preserve like the weight, the value of the CSP on every possible assignment with some like reweighted sub-instance.
Louis, I have a question here.
Yeah.
So is the goal here to get a deterministic sparsification? Because like a random sparsification is like quite easy, right? You just subsample every edge with some probability. You only have like, I mean, you can subsample just random order and edges from the cut or something, and then that still preserves like every,
yeah. So the point, if you do a random subsampling, just with like everyone getting the same sampling rate, this will only preserve it up to an additive error. And here we're trying to preserve the value to a multiplicative error. So for instance, imagine there's like some assignment which for only a single constraint evaluates to 1. If we want to preserve that to multiplicative error, then we have to keep that constraint no matter what.
I see.
Yeah, we can't do like a global single sampling rate. We have to like somehow do a more refined analysis of how much emphasis we put on each constraint.
I see. Okay, that makes sense. Thanks.
Yeah. No, but that said, it's still also a very good question, like to get deterministic sparsifiers. I mean, we don't know how to do that, but it's also a very important question.
Thanks.
Yeah. And so, this perspective as a CSP also captures, for instance, what we were looking at with hypergraphs. So for instance, if we consider a hypergraph of arity R, and this arity just means every hyperedge is of size R, we could instead define a CSP where the predicate, and by predicate before this was the 2 XOR. Now we're just going to look at a different kind of function. The predicate would be of arity R, again, just working on R variables, and we could just set it to be the not all equal function. So in particular, if we looked at this hypergraph on the bottom left, every hyperedge here is of size 3. If we again give this kind of canonical assignment, everyone in the set S gets value 1, everyone outside gets value 0. A hyperedge is cut if and only if some hyperedge has some 1 and some 0 somewhere in the hyperedge. That's to say it's not completely all 1s or completely all 0s, which would mean it's stuck on one side of the cut. So naturally, then, if we look at this not all equal constraint, this is exactly capturing whether a hyperedge E is going to be cut by the set S. The task of hypergraph sparsification is then to choose like a reweighted sample or a reweighted subset of these constraints such that for every assignment, we're preserving the weight of the satisfied constraints to like a 1 plus or minus epsilon multiplicative factor. More broadly, though, so we've only looked at like 2 possible like functions to apply in each hyperedge, like the 2 XOR and this not all equal function. More broadly, one might wonder, in general, for which possible functions P. So again, P is going to be like this predicate that we're applying to each hyperedge. For which predicates P, can we always get like sparsifications? In general, like these functions P don't have to be well behaved. They can be very like arbitrarily complex functions. And so it's a very natural question to ask, in what circumstances do these enable sparsification, like no matter which variables they're operating on. So one way to think about this is kind of like some natural examples is that what we were looking at before is that we're considering a hyperedge E to be cut if and only if there's at least one vertex in S and one vertex in V minus S. We could also consider a hyperedge to be cut perhaps if we want 2 vertices in S and 2 vertices in V minus S. Perhaps we want some kind of robustness where if there's just one vertex that's crossing this cut, then it's not a big deal. But if there's 2, then maybe we actually want it to be considered cut. We can also consider more like arbitrary notions of a hyperedge being cut. For instance, maybe we care about the parity, like if there's an odd number of vertices in the set S, or if we just want to look at whether the hyperedges are being like split perfectly in half, right? Maybe it's a hyperedge is cut if and only if the edge isn't being perfectly split in half. So there's lots of like natural like splitting functions that we can apply to each hyperedge to consider what characterizes this edge being cut. And in particular, these are all examples of a very nice class of functions, which are called like symmetric predicates, in the sense that these predicates only depend on like how many vertices are on like the one in this hyperedge on one side of the cut. And that's to say this predicate P that we're applying to each hyperedge depends only on like the magnitude of the string that it's operating on. And it turns out, in this setting is where we're going to get some very nice results today. In particular, like the natural question that we're going to ask is, suppose we're working with these symmetric predicates. In general, for which CSPs, for which of these predicates, will CSPs using this predicate always be sparsifiable? And in particular, we want to characterize, to what size they're sparsifiable. So are we looking at something that's near linear in the number of variables, quadratic in the number of variables, cubic in the number of variables, etc. And so what we've seen is this is already capturing a very large variety of functions. In particular, it's capturing these cut functions in graphs, cut functions in hypergraphs, these kind of more arbitrary definitions that we discussed here. So it is a very natural question to kind of push this kind of hypergraph sparsification to the limits and see what exactly is possible. And it turns out that there's one kind of underlying number theoretic property about these symmetric predicates that arises, and which almost like entirely governs their sparsifiability. So I'm going to introduce this property, and then I'll be able to say like the main theorem that I'll prove today. So in particular, the property that kind of governs sparsifiability is called periodicity. So again, we'll be given some predicate P. It's a predicate of arity R, so it's operating on R variables. And we say that P is periodic if the levels of the predicate where it's 0 are evenly spaced. So I have some examples because it's a slightly weird definition. So the mathematical definition is that there exist integers a and b, such that p of y is, 0 if and only if magnitude y plus a equals 0 mod b. So if we look at this in terms of examples, like the 2 XOR function, we would consider to be periodic. The period is 2 because every even number, the XOR function will evaluate to be 0. So if we parameterize this in terms of the levels of the function, when it's an XOR operating on a bit string of weight 0, it'll always evaluate to 0. When the weight of the string is 1, the XOR will evaluate to 1. When the weight of the string is 2, it'll again evaluate to 0, because we're just measuring the parity of this bit string. If we look at the not all equal function, this is going to be periodic with period r, in the sense that it's 0 at the 0th level and then 0 at the rth level and 1 everywhere else. So we would define this as periodic with period r. And again, we can look at this, instead of looking at the 2 XOR, we can look at the r XOR. And again, this is periodic. It'll be 0 at every even level. And I guess, okay, so what's not periodic? So what's not periodic is something like this 2 and function. So here, right, we're 0 at the 0th level and the 1st level. And this would kind of establish the period. The period would have to be 1 in this setting. But somehow we're getting a violation here because the period is 1, but then when we go from level 1 to level 2, all of a sudden, it's going from a 0 to a 1. Like the predicate is satisfied at the 2nd level, even though it's unsatisfied at the 0th level and the 1st level. So it's a little bit of a weird definition, but it's essentially just measuring, like, are the zeros of the function perfectly periodic? And if there's anywhere where the zeros are not perfectly periodic, then we say it's not a periodic predicate. And kind of the amazing result that comes out of this definition of periodicity is that it completely characterizes when CSPs are sparsifiable to linear size. So in particular, if P is a symmetric and periodic predicate, then every instance of a CSP that uses this predicate P is 1 plus or minus epsilon sparsifiable to a near linear number of constraints. But if the predicate is symmetric and not periodic, then we're guaranteed that there exist instances which require sparsifiers of at least quadratic size in the number of variables n. So an immediate corollary of this is that it kind of gives a nice lens to understand all this prior work on graph and hypergraph sparsification. Because at face value, it might have seemed a little arbitrary that these kind of natural definitions of sparsification that we adopted all led to linear size sparsifications. And one way to interpret this is that the reason this happened is that we just happened to choose predicates, which were, okay, symmetric is a very natural definition to have. But these predicates we chose just happen to be periodic. And if something's periodic, it will always enable sparsification. So yeah, I mean, it's a little bit surprising perhaps that we actually get such a clean understanding of why we get these linear size sparsifiers, but nevertheless, we can also apply it downstream to other sparsification tasks. For instance, one consequence is that we can also look at these larger arity XOR constraints. And we can still sparsify these systems. So for instance, another corollary is that XOR CSPs are always going to be sparsifiable to near linear size. And then one other remark, which is not going to be shown in the theorem, and which I probably won't have time to go through the details or the proof today, is that the sparsifiers, which we guarantee to exist, we can actually even compute them efficiently, in the sense that we have these probabilistic polynomial time algorithms which can compute the sampling rates and construct a sparsifier with high probability in this setting. So if there are any questions like that, please don't hesitate to ask. But this is kind of the main result that I want to talk about today, at least provide context and explain some of the applications. So if there are no questions, I might just briefly mention how the second result comes about and why it's an interesting new combinatorial consequence of this theorem. So specifically, I'm going to mention how these XOR CSPs actually yield what we call Cayley graph sparsifiers for a very natural definition of Cayley graphs. So first, I'll just recap what Cayley graphs are. So again, a Cayley graph is just a graph G where the vertex set is associated with some group. Here, we'll just be looking at a very simple example. The group is just f2 to the n. So we're just looking at all length n bit strings. And each bit string of length n is associated with some vertex. A Cayley graph is just parameterized by some set of generators Q, which is some subset of f2 to the n. And we say that two vertices are connected if and only if their difference is in the set Q. So here, if we just look at, like, if we wanted to generate the hypercube,
Lytton, can you hear me?
Yeah, I can hear you, I think.
Okay, I was worried if it was my Wi-Fi.
Yeah,
Oh,
no problem.
okay. Maybe let me pause the recording for now.
yeah. Again, so we were just defining what a Cayley graph is. And so a Cayley graph, yeah, the vertex set is associated with some group. Here it's just going to be length and bit strings. And then we associate it with some set of generators. And two vertices will be connected if their difference is in the set Q. So again, if we define the set of generators to be at least length 1 bit strings, then it's just generating the ordinary hypercube. We could also choose like an arbitrary set of generators, and the set of generators can be as large as 2 to the n, because there's like 2 to the n possible elements in f2 to the n. So, I mean, this is just defining some arbitrary graph. Naturally, then you can create a cut sparsifier for this Cayley graph. There's going to be 2 to the n vertices, so the size of the cut sparsifier, like the number of edges, would be something like 2 to the n over epsilon squared. But the problem is that this definition of a sparsifier is not guaranteed to still be a Cayley graph, in the sense that the way we compute just an ordinary cut sparsifier is that we sample every edge with some probability, but we're not paying respect to this clean generating structure, in the sense that it won't always be the case that if some edge is connecting vertices u and v, then this difference u minus v will always be like an edge coming out of every single vertex. Right, this will just be some haphazard sampling, and there won't be a concise description of the resulting sparsifier that we get. So a natural question would be, can we build Cayley graph cut sparsifiers over, say, f2 to the n, such that the sparsifiers are still Cayley graphs? And it turns out that using XOR CSP sparsifiers, this is actually something that we can do. And to the best of our knowledge, this wasn't something that had been established before at any point. So in particular, that is to say that using XOR CSP sparsifiers, we can sparsify any arbitrary Cayley graph over f2 to the n to a generating set of size O tilde n over epsilon squared, while preserving all 2 to the n possible cuts in the Cayley graph to a 1 plus or minus epsilon factor. So somehow the language of the CSP sparsification enables us to capture like more complex data structures, and still, kind of as a black box, conclude their sparsifiability. And that's why abstracting to this more general framework of like CSP sparsification, has led to like more powerful results, and is kind of motivates a nice perspective to use for these results.
Louis, I have a question.
Yeah.
So this generating set, is it like a subset of the original generating set, or is this something else? Or
yeah, it'll be a subset of the original generating set, just where to kind of compensate for the fact that it's a smaller set, some of the generators will be like weighted, like have some weights associated with them. Exactly.
Okay. Sounds good. Thanks. Yeah.
Yeah, perfect. Yeah, so with that established, then I might start talking like kind of a little bit about the intuition for the proofs. Hopefully you can see that this is kind of developing a bigger, broader framework for CSP sparsification. And the CSP sparsification has applications to kind of a wide variety of natural combinatorial problems that may appear. So in particular, I'll first just talk about kind of the upper bound. It turns out that the lower bound, it's not too interesting. It comes from a kind of very natural like reduction. So instead, I'll just focus on the upper bound. So just to remind you, what we want to focus on is that if some predicate P is symmetric and periodic, we want to show that every CSP instance phi is 1 plus or minus epsilon sparsifiable to like a near linear number of constraints. And again, the way we had defined a symmetric predicate is that there exist these integers a and b, such that p of y is 0 if and only if magnitude y plus a is 0 mod b. And again, here we're establishing that b is the period. In general, like this period can be an arbitrary number. It could be like anything from 0 to R. Because we're just going to focus on like a special case, all we want to do is build intuition for how the proof is going about. We'll focus on a very simple case, just when B is 2. And I guess I should say it's actually not as simple as we'd like it to be. It still involves like a lot of complicated techniques. But when we're focusing on B equals 2, all we're going to be looking at is just like the R XOR function, essentially. Because we have a predicate of arity R, and if the period is 2, we're either saying, it's either only 0 for like even weight strings, or it's only 0 for odd weight strings. So this is essentially just, simulating some kind of, R XOR function. It turns out that when we look at this R XOR function, it actually has a very nice kind of canonical representation with like linear error correcting codes. And I'll define these on the next slide, and then to kind of explain why this relationship is kind of a nice thing to work with. So an error correcting code C is just defined to be an n-dimensional linear subspace of f2 to the m. And the way we can specify an error correcting code C is with a generating matrix G in f2 to the m by n. And we say that this code C is basically just like the span of this matrix G. So in coding theory language, we say that X, kind of this vector X, is the message. G is kind of the encoding matrix. So when we multiply G by X in this typical matrix vector product over F2, this yields a code word. And the weight of a code word is just the number of non-zero entries. And so this is a lot of definitions, but it'll all become more clear when we look at the next slide and how this is like a canonical relationship with like CSPs. So if we go back to this example of just like a graph with vertices and edges, turns out that there's a very nice error correcting code that we can like associate with this graph. In particular, for every for every edge in this graph, every edge UV, we create a matrix where there's a single column for every vertex, and for every edge, we add a row which has 2 ones corresponding to like the endpoints of that edge. So here, if we have an edge between vertices 2 and 3, we add a row where there's 2 ones, one in column 2 and one in column 3. So again, we'd already seen the correspondence with kind of an XOR constraint. So at the bottom right, we had this XOR constraint, which was X2, XOR X3. And the way to think about it is that all we've done is kind of encoded this as a row inside of some generating matrix. The reason this is a nice representation is that if we consider some assignment X in 0, 1 to the n, this is kind of equivalent to looking at some matrix vector product. In particular, if we made the vector where it was just x1 through like x5 in this example, and did the matrix vector product where we took B and multiplied by this vector X, this will kind of like canonically give us the exact same CSP that we have on the left. All we're going to do is we'll be taking x1, XOR it with x2. This becomes the top row of like the resulting vector. And you can check like this relationship will hold in the sense that like every single row corresponds with some constraint here that's like an XOR. So kind of naturally, this means that for any arbitrary assignment in 0, 1 to the n, the number of satisfied constraints in this CSP on the left will actually equal the weight of the corresponding code word that we get by multiplying this matrix B by the assignment vector X. And this doesn't just stop right here. We're looking at like edges, so it's kind of defining like an XOR constraint of arity 2. This doesn't just stop with arity 2. In general, if we had considered some XOR of arity 3, again, this would be a relationship we would have. In the sense that if we're just taking the XOR of x1, x2, and x4, we can just add a row which has ones in the corresponding positions. And when we take the matrix vector product, it's kind of just canonically taking the XOR of these elements. In a sense, all an error correcting code is doing is just it's picking out a couple elements and deciding to take their XOR. And in error correcting code literature, this is to build like redundancy, so you can recover against errors. Here, it's just because we're modeling some CSP, and we're not really too concerned with like the properties of how good the error correcting code is. But yeah, again, in this case, we would again have this relationship that for any assignment x in 0, 1 to the n, the number of satisfied constraints in C would equal the corresponding weight of the code word BX. So kind of this work, for instance, on graph cut sparsification is equivalent to a result saying that when a generating matrix has, two ones in every row, there exists like a reweighted subset of the rows of this generating matrix, which preserves like the weight of every assignment to a 1 plus or minus epsilon factor. A natural question then is, if we're given an arbitrary generating matrix G, will this still always be the case? In the sense that, so we know this is true when there's 2 ones in every row of the generating matrix. If there's an arbitrary number of ones, like even starting at 3, this is unknown. Can we actually still sparsify these generating matrices? And the definition of sparsification that we're interested in is that we're choosing a reweighted subset of the rows of this generating matrix, such that for every possible assignment X in F2 to the N, the weight of the corresponding code word with this kind of like submatrix is preserved to a 1 plus or minus epsilon factor when compared with the original code word. And this is what we call like a code sparsifier or code sparsification. Hence, this is a kind of the key technique that we use in deriving the CSP sparsification results, as kind of alluded to by the title. The main theorem that I'll kind of try to give you intuition for in the last little bit of this talk is that, yes, this is actually like a general phenomenon. In general, every generating matrix G can be sparsified to like a reweighted subset of the rows of near linear size. So in particular, what this is saying that for every code word, there's some like same set of coordinates that we can subsample and possibly like increase their weights, such that on this subsampled set of coordinates, the weight of every code word is preserved to 1 plus or minus epsilon multiplicative factor. An immediate consequence is then, okay, if you had only been interested in these CSPs on symmetric predicates where the period was 2, this would automatically, give us the result that we were looking for. But I mean, more generally, we cared about other periods, and maybe at the end, I'll give you just a slight word about how we can use a similar technique for other periods. But at least we can see that here if we can solve this problem, we've addressed a non-trivial subset of these kind of symmetric CSPs. So next, I'll try to give you just a little bit of intuition for the proofs. So what I'll plan to do is I'll probably discuss a little bit of these like Benchur-Karger type proofs. In particular, I'll try to give a very concise description of how we can get these like cut sparsifiers for graphs. Because again, the cut sparsifiers for graphs are addressing a specific instance of these generating matrices where every row has 2 ones in it. So it turns out that like the key result, and again here in graph sparsification, the goal was to preserve the weight of every cut with like a reweighted subgraph. And it turns out that the key tool that's used in these sparsification results is something that's called Karger's cut counting bound. And in particular, it's saying, okay, if we're given an unweighted graph G, and any parameter alpha, which is a positive integer, then the number of cuts of size less than or equal to alpha times the minimum cut of G is at most n to the 2 alpha. So the way to interpret this is that it's some kind of smooth counting bound, in the sense that if we just look at the minimum cut, this will tell you that there's at most n squared minimum cuts. But now maybe we're curious, okay, how many near minimum cuts are there? How many minimum cuts are within, or how many cuts are within a factor of 2 of the minimum cut? This would tell you that it's still bounded by some polynomial. It's bounded by n to the 4. So the number of cuts that are within a constant factor of the minimum cut is bounded by some polynomial. And more generally, there's kind of a smooth bound on the number of cuts that can be within some factor of the minimum cut. So we're getting like a smooth bound of like how many small cuts can be in this graph. An immediate consequence of this is that if we were to look at a graph G and say that the minimum cut is a value D, now we actually can do random sampling. In fact, we can randomly sample at rate roughly 1 over D and correspondingly reweight the edges that we sample by a factor of roughly D. And this will yield a sparsifier for the graph G. And this is just because we can take a Chernoff and union bound over every cut in the graph. And because we have this nice counting bound, we know there aren't too many small cuts. And the small cuts is where we'd be most worried about a Chernoff bound not giving us a high probability result. But now it'll survive the union bound because the union bound isn't too big. So in general, for every parameter alpha, kind of getting a trade-off between how many cuts there are and also the concentration bound that we'll be getting from Chernoff. And it turns out that this statement alone is already going to give us like a very nice understanding of where graph cut sparsifiers are coming from. So in particular, let's look at an example. Our worry would be that, we're given an arbitrary graph G, and the minimum cut is pretty small. Because if the minimum cut is small, it means we can't actually, sample the edges at any, small rate. We'll be forced to keep many edges. In this graph, for instance, the minimum cut is value 2. So this would say, okay, maybe you can even sample at rate 1/2, but there's actually log n's that are hiding there, so you wouldn't even be able to do that. But somehow, the graph structure itself should still be amenable to sparsification because we have these cliques on n/3 vertices, which are very connected. And like on their own, they should be sparsifiable. So the question is how we can still sparsify this overall graph, even though it has some first order bad structure. So let's try to do maybe just the obvious thing. We take this graph, we find a minimum cut, and the size of the minimum cut is 2. So let's just decide that we take those 2 edges and we remove them, and we'll just store them, explicitly. We won't do any sampling on those edges. We just keep them exactly. Now we look at the rest of the graph, see if there's any small minimum cuts anywhere. Now there's even a minimum cut of size 1. So again, we'll just take this edge, we'll remove it, and we'll store it exactly. And now what do we get? So we get a set of graphs, each of size n/3, which are extremely well connected. So in each of these components, the minimum cut would be n/3. And so we could definitely, sample these at rate, maybe log n/n or something, while still preserving all the cuts in these graphs with high probability. And then on the other hand, we have a graph where we removed all these, minimum cuts that were too small. This graph isn't particularly big, but here we certainly can't hope to do any kind of sampling. But in general, in this case, we could just downsample this graph on the left at rate roughly 1/n, and then just keep this graph on the right explicitly and take their union. And this would give us a sparsifier for the original graph, which has only a near linear number of edges. So it turns out that this is actually a general operation that we can perform. So we can choose some parameter d to kind of parameterize the minimum cut. And we'll let G less than or equal to D just be the result of iteratively removing all edges in G that are involved of cuts of size less than or equal to D. And a clean bound that we can see is that the size of this graph is always at most n-1 times D. And the reason why is that what happens in the first iteration, say there's a minimum cut of size less than or equal to D, we take all those edges and we remove them, but the number of connected components in the graph has now gone up by 1. Because we removed some cut, it disconnected the graph into 2 parts. Now, if we repeat this again, we find some minimum cut of size less than or equal to D, we take those edges and we remove them. This will split one of these other components into 2 parts. So again, the number of components is always going up by at least 1. And the number of edges we're storing in each such iteration is at most D. So in particular, because it can only be at most n connected components, this can only happen at most n-1 times before everything is just an isolated vertex. So this means the size of this graph G less than or equal to D has to be at most n-1 times D. So it turns out that this is already going to give us a mechanism for sparsification. So the minimum cut in, we start with the graph G, and right now we'll just parameterize in terms of this this cut value D. So you split the graph into 2 parts. On the one hand, we kind of iteratively remove all cuts of size less than or equal to D. This gives us the graph on the left, which was called G less than or equal to D. And then G greater than D is just everything else. The key observation is that G greater than D, every single cut in G greater than D is at least size D. So in this graph, we can afford to downsample, sample at rate 1/D. The graph on the left, G less than or equal to D, there's no guarantee on any kind of sampling that we can perform. But we do know that the number of edges is kind of fundamentally bounded in this graph. So what do we get? Starting with as many as order n squared edges, we get 2 graphs. We get G less than or equal to D, which is order nd edges. And then this downsampled version of the graph on the right, which has roughly n squared over d edges. And the reason it's n squared is because g greater than d can have as many as n squared edges, but then we can afford to sample at rate 1 over d. If we just balance the parameters here, we see that if we set d to be square root n, then this will just yield a sparsifier for g with order n to the 3/2 edges. Because we just take the union of these two resulting graphs. And now we can just reapply this logic, right? So what do we have? We have some graph that has n to the 3/2 edges. We'll just do the same procedure with d equals n to the 1/4. So we'll pull out all edges and minimum of cuts of size less than or equal to n to the 1/4, and then downsample the rest of the graph at rate 1 over n to the 1/4. And this will now give us 4 graphs that have order n to the 5/4 edges. And again, the union of all of these graphs will be a sparsifier for g. So this is just defining some recursive process, where at the very bottom level, we're going to take the union of all of the leaves. So in particular, if we were to check all the parameters in the ith level of recursion, we're getting 2 to the I graphs, each of which has order n to the 1 plus 1 over 2 to the I edges. And it turns out that we can just do this for log n recursive levels. And this will then return a sparsifier for g of size O tilde n. So this is a completely, correct implementation of creating a cut sparsifier for a graph. And it turns out that this framework, well, not exactly, but at least partly will be amenable to error correcting codes. And that's what I'll talk about briefly now. So in particular, the preceding algorithm works because of this cut counting bound, right? So what we were using is that the number of cuts of size within a constant factor of the minimum cut is always bounded by some small value. And this is what enabled us to do this sampling procedure in the graph after we had removed all of the minimum cuts. So the analog of a minimum cut, kind of in the coding theoretic sense, is what's called the distance of a code. And it would just be the smallest weight of any code word in the code. So again, we have this generating matrix G, and the span of the generating matrix is just a bunch of vectors in some f2 to the m. The distance of the code would just be the minimum weight of any vector, any non-zero vector in the span of this matrix G. So what we would have liked to hope is that perhaps a direct analog of Karger's bound does hold in this coding theoretic sense, in the sense that perhaps there aren't too many code words that are within a constant factor of the minimum weight code word. It turns out that this is actually patently false. In particular, one of the crown jewels of coding theory is that you can actually construct codes for which this is not false because they give the best error correction. So for instance, if we consider any asymptotically good codes, it doesn't quite matter what these words mean, but what we'll have is we'll have an exponential number of code words, all of which have their weight within a constant factor of the minimum weight code word. And in particular, this would mean that we couldn't hope to do any kind of sampling as Karger does. Any kind of sampling like this will have to oversample by too large of a factor that we couldn't hope to get linear size sparsifiers. So somehow we need a modified cut counting bound. And to do this, the key observation is that what we actually used in graphs, it wasn't just that the cut counting bound holds. It was that there exists a set of edges that we can remove such that the cut counting bound holds. Right, what we had said is for a parameter d, there exists a set of less than or equal to nd edges, such that if we remove these edges, the resulting graph satisfies this counting bound with parameter d. And it turns out that for this statement, there actually is an analog for codes. And this is one of the main kind of technical, intricate contributions of the paper. So informally, what we're saying is for every code of dimension n, you can remove at most nd rows of the generating matrix, such that the resulting code satisfies this counting bound with parameter d. Mathematically, what this looks like is we're saying for any choice of this parameter d, that's a positive integer, and any error correcting code c in f2 to the m, there exists a set S, where S is just a subset of the rows of this generating matrix, where S is bounded by size n times d, such that once we remove the set S, so here we're restricting to C, restricted to S bar, the number of code words of small weight in this error correcting code satisfies a similar counting bound to what Karger had. So again, Karger's was n to the 2 alpha. Here we're getting 2 to the alpha times n choose alpha. These are like roughly on the same order. You can think of them as being basically the same. Kind of a visualization is, again, we had this generating matrix G. And off the bat, this generating matrix G, it will have too many code words that are within a constant factor of the smallest code word. All we're saying is that there exists some set S of rows of this generating matrix, such that once we remove these rows, the rest of the matrix is satisfying some nice sampling property, right? But the way to think about it is that we remove this set G restricted to S. For the rest of the matrix, G restricted to S bar, everything is very well behaved, and we can do a similar sampling procedure as Karger did for graphs. And it turns out, okay, now we can just do exactly the same kind of recursive breakdown that we had before, right? We start with the code C. We break it into C restricted to S and C restricted to S bar. On C restricted to S bar, we can do this random sampling at rate roughly 1 over D, because this is the guarantee that we're getting from the lemma. If we balance parameters, all that we have to do is we set this parameter D to be like square root m over n, and it will follow that we can take the union and get a sparsifier for C. And again, if we just balance out all the parameters in this kind of recursive tree-like structure, if the starting length is polynomial, then we can just take, again, roughly log n levels in the tree, take the union of all the leaves, and this will create a sparsifier for the original error-correcting code C.
Louis, I have a question.
Yeah.
So do you assume anything about the structure of the generating matrix, or is it true for any generating matrix?
Yeah, this is true for any generating matrix. But so the only choice we have here is for the parameter D. But yeah, this is true for any arbitrary generating matrix. And not only that, we can also, we have like an efficient algorithm for computing a decomposition like this. In the sense that we'll say, okay, here's the bad set of rows, or at least like a superset of the bad set of rows. Here's the rest of the matrix, and now you can do the algorithm efficiently even. But yeah,
Nice.
there's no conditions in the statement. Yeah.
Thanks.
Yeah. So once we have the statement, though, it's hopefully it's clear to see that we can really do the exact same procedure that like Bencher and Karger had done in their paper. So really, they had done a different procedure, but this is kind of one interpretation of what they had been doing. I guess I won't actually go into the details of how we can prove this code counting bound, but maybe I'll just give some intuition. The way this follows is that we define a kind of randomized algorithm, which will output code words that are in the span of the generating matrix G. And what will happen is that any low-weight code word will be returned with higher probability as long as some underlying condition is holding. And if low-weight code words are returned with higher probability, this means there can't be too many low-weight code words. Right? So this will implicitly give us an upper bound on the number of low-weight code words just by like preserving probability mass. But the number of, so there's kind of like a clean trade-off between the weight of the code word and the probability that this algorithm will return it. And because the algorithm can only return a single element at a time, the sum over all elements of the probability of being returned has to equal 1. So in particular, as long as this underlying condition holds, we're getting some nice trade-off, which will directly give us a statement like the above, which says, the number of low-weight code words can't be too large. And there's a smooth trade-off where the number of slightly higher weight code words, it can be a little bit higher, but not too much higher. And this is all just coming because we're like preserving like probability mass. As you can see, there's one condition that we were saying. I'm being very vague about this, but this is all holding as long as some underlying condition about the code is true. If this condition fails, this is actually giving us like a witness to the fact that there's a bad set of rows somewhere which has to be removed. So if this condition fails, we just remove the bad rows, and this is how we actually create the set S of rows that we have to remove. And it turns out that we'll still have some nice property that this set S will not be too large. So just for a summary, what do we have? We have this code counting bound, which says you can always remove rows from the generating matrix, such that the rest of the generating matrix satisfies a nice counting bound. And this gives us a theorem which says, for any code C of dimension n over f2 to the m, there's a reweighted subset of rows of this generating matrix, which preserves the weight of every code word to a 1 plus or minus epsilon factor. And by this relationship to CSPs, this directly gives us a statement that for any CSP with a predicate of period 2, there exists a reweighted set of O tilde N over epsilon squared constraints that preserves the weight of satisfied assignments on every x in 0, 1 to the n. So here, hopefully the relationship is clear. We kind of started with a CSP. This then leads to coding theoretic representation. And now in the language of coding theory, we're kind of able to establish the existence of sparsifiers. And everything here kind of was a bijection, so it translates to the CSP world as well. I've kind of been very vague, and we only talked about period 2. It turns out that this coding theoretic perspective will work for any prime period. In general, codes are defined over arbitrary fields FQ. So for any period P, we'll be able to do this kind of sparsification result. What's left then is to kind of use a different technique for non-prime fields, or it's like non-prime groups. And here it turns out that we can, with like more complex machinery, we can do like a lattice theoretic perspective to deal with predicates that have a non-prime period. As for lower bounds, these roughly follow from predicates that have ands inside of them. And the observation is that the and predicate requires large sparsifiers. The reason why is that if you, for instance, consider the to and predicate, and consider the to and predicate applied to every single pair of variables xi, xj, this will necessarily require sparsifiers of quadratic size. So the reason why is that if you query with the assignment, which is has 2 1s corresponding to xi and xj, only a single constraint will be satisfied. The only constraint that will be satisfied is the and of xi, xj. Every other constraint will have some 0, like some xk will be 0, and so that and will evaluate to 0. So if you want to preserve the value under any assignment, you have to keep every single and constraint. The final comment was just that these techniques have also led to classifications in different regimes of CSPs. Here we were considering like symmetric and periodic. It turns out that we've been able to use them to classify when predicates are amenable to non-trivial sparsification. So kind of a trivial sparsifier would be of size O of n to the r, because there's n choose r possible r tuples to apply the predicate to. It turns out that we can give an exact classification when predicates are sparsifiable to size O of n to the r minus 1. We've also been able to, for small r, we've also been able to give an exact characterization for all predicates, what the best possible size of their sparsifiers is. And this is all coming through this kind of coding theoretic perspective. The final thing would just be some open questions. A general classification for all CSPs is a big open problem. Likewise, getting linear size, everything today was near linear size. And this kind of ties in with what Santoshini was asking, whether you can even get deterministic sparsification results. These are all like open questions. And yeah, kind of we're at the very beginning of opening this line of research. So hopefully some of these questions will be answered soon. And that should be all from my end.
Thank you so much, Louie. That was a great talk.
Thank you. Thank you. Yeah.